In this video, I want to talk about a first application of a spectral sequence, so in particular the Bockstein spectral sequence. And remember, the whole point of building up all of this machinery is ideally to learn something. So this will be the first time we get to take something away from a spectral sequence. And I hope we'll be doing that a lot more in this course. But let's remember where we are. So our Bockstein spectral sequence came from this exact couple, where we started with D1 is the cohomology of our space X and integral coefficients. And so I have that here as well. And this map over I is really just multiplication by P. E1 is going to be the cohomology of X with mod P coefficients. So remember, P here is a prime. And J is just reduce mod P. And then here, our K was really beta, our original Bockstein homomorphism, the connecting homomorphism in the long exact sequence. And then we said D1 is just J after K, as always in an exact couple, but that turned out to be delta 2, our other version of the Bockstein homomorphism, really just composing beta with reduced mod P, as we can see from this diagram. And then I think of dr as do J after doing I in reverse, R times, and then doing K, and that's a little bit of a lie, so put that in quotes. Okay, and maybe let me also remind you how this all fit in to a diagram. So we have our long exact sequence in cohomology, where this is times P, and then we reduce mod P, and we get the cohomology of X in mod P coefficients, and then our connecting homomorphism comes in, that's our beta, increases the degree by 1, and goes to the cohomology of X, and so on. And we could sort of slip delta 2 into this diagram by just reducing mod P, and so here's our delta 2. Okay. Now, remember from your algebraic topology course that we have this universal coefficient theorem, and that tells us how to find the cohomology of a space with coefficients in an abelian group A from the homology. So we hom from the homology into our abelian group A. But then there's this correction term, x1, from the homology 1 degree lower down. And we take x with A. And for our purposes, we're going to say that we'll take A to be a copy of the integers, so we can get cohomology from homology, or we can already see we want something about coefficients with mod P, so also Z mod P. Okay, and we want to use this coefficient theorem together with the Bockstein spectral sequence. So I need a little bit more setup here. If we look at the homology of X, and this is some finitely generated abelian group. This will happen, by the way, whenever, say, X is some CW complex, which I was assuming, and it's finite type. Okay, well, then a finitely generated abelian group has a nice decomposition, so I should get a direct sum of some number of copies of the integers. So that's the free part, and then I should also have the torsion piece, and the torsion piece, of course, looks quite nice. So we have Z mod some prime to some power, and these are not necessarily distinct, but Z mod other primes potentially to other powers, so on. Okay. So what we want to do is sort of compare what the homology of X can tell us about the cohomology in different coefficients. So using that universal coefficient theorem, if we start with a copy of the integers, and we see that it's a direct summand. Oops. Of the homology, say nth homology, then the universal coefficient theorem is going to give us a copy of the integers as a direct summand of the nth cohomology, and it'll also give us a copy of the integers mod p in the cohomology in mod p coefficients. Okay, so really what I'm saying here is just hom, there's no x terms. But if we start with a copy of the integers mod p, maybe mod p to some power, z mod p to the k, and this is a direct summand. Of the nth homology. Well, now our universal coefficient theorem's a little bit more interesting. So we'll get a z mod p to the k in the n plus first cohomology of x, right? When I hom to z, I don't get anything, so I only have this x term. So this is coming from x. And then when I work in mod p coefficients, I'll get a z mod p in a couple of places. So the first one is in degree n. But then the x will also kick up a copy into degree n plus 1. Okay, so that's also coming from an x term. Okay, great. So what's the point of all of this? Well, the idea that we're after, and you probably played this game to some degree in your algebraic topology course, is if we see a copy of the integers mod p in the cohomology of x in mod p coefficients, and we want to know about the cohomology in integral coefficients, how can we tell where it came from? Oops, trying to skip parts of words. Where did it come from? Okay, so I look at both of these, and in mod p coefficients, I see a z mod p. So how can I tell the difference? Well, of course, if there's no z mod p in degree n plus 1, then it certainly isn't the second case. But how can I figure out if there is a z mod p in degree n plus 1? Was that two copies of the integers that led to those two z mod p's? Was it a copy of z mod p to the k? What power of k was that? So on. So that's the game we're going to play here. And we'll use the Bockstein spectral sequence to help us out. Okay, so first we need to notice that if we have some element in the cohomology of x in z mod p coefficients, let's call that element A. If this comes from an integral class, then the differential on any page will be 0. So dr of A is 0 for all r. Okay, and we can see this pretty easily because we look at this long exact sequence in homology, cohomology, I suppose. Whoops. That was our multiplication by p, then we reduce mod p. Then we've got our connecting homomorphism. All right, I didn't quite leave space for the same diagram I wanted to have before. That's smart. I would have just copied and pasted when I had it. But here, this is reduce mod p. This is our beta connecting homomorphism, right? And this is our other Bockstein. It's just the composition of those two. So what do I mean if it comes from an integral class? Well, really I mean if there's a class here in Hn of x in mod p coefficients, but it came from a class back here, maybe I should call this one a bar because I've reduced mod p. Well, then as soon as I apply beta, I'm going to get 0 because this is a long exact sequence. So of course, delta 2 is going to be 0. That's my d1 differential. Maybe another way to say what I mean here in sort of the language of the exact couple is that I think of my dr differential as doing j after I in reverse r times after k. And so I do dr to something that came from the integers. So j was the thing that took me from the integral coefficients to the mod p coefficients. So if it's in the image of j, well, then really I'm doing j after I in reverse r times after k after j of a. And of course that's 0 because k after j is 0. So the moral of the story is just by exactness, of course, I get 0. Okay, but maybe a little bit more interesting is this proposition, which says, say we take some class. I want to think of it as coming from an integral class, but in a particularly nice way. So let's say it generates a copy of the integers as a direct summand of, well, this is going to be a direct summand of the nth cohomology of x. So I start with something in the nth cohomology. I'm looking at what this does in mod p coefficients. I run the Bockstein spectral sequence, and I see that when you take it mod p, so that's my a bar, dr applied to it is 0 for all r. Okay, we just said that because it came from an integral class. This is just a special kind of integral class. But also, this thing is not in the image of the differential for any r. Now, part 2 of this proposition is, suppose we take some class b, and instead this generates a copy of z mod p to the k as a direct summand and now, a little bit awkwardly, I'm going to make this a direct summand of hn plus 1 of x. Well, then the claim is that we see this in the spectral sequence by having some b bar. Oops. This is going to generate a z mod p inside hn plus 1 of x in mod p coefficients. Okay, we know that the z mod p to the k gives rise to a z mod p. I'm just naming the generator. And I want a b tilde in z mod p as a summand of hn of x, in mod p coefficients. Okay, so these are summands, direct summands. And I'm really just trying to name the elements properly, but I just want to think about b in a sense. So the idea is that dr of b tilde is 0 for r less than k, and dk of b tilde is b bar. Okay, so I want to say this in a couple different ways. First, what I mean, and then talk a little bit about the proof. Well, okay, maybe let me draw this picture first. So I want to look at the cohomology of x and the cohomology of x in mod p coefficients. And I'm going to look at the nth degree and the n plus first degree. And of course, if I have a copy of the integers in degree n in the cohomology of x, that's going to give me a copy of integers mod p in the cohomology of x in mod p coefficients. And all the differentials on this thing will be 0. So all the Bockstein differentials are going to be 0 because these came from integral classes. So we already said that. Now, if I look at having a copy of, say, z mod p, well, what this is telling me is I should have a z mod p and another z mod p that's coming from the universal coefficient theorem. Oops, and I'm going to need more space. And they're connected by a d1 differential. So that's what I'm trying to say here with this b tilde, b bar stuff. Okay, and then how will I tell that that's different from the situation where, struggling with my pencil today. How do I tell that that's different from the situation where I had z mod p to the k in the cohomology of x? Well, I look over here, and again, I'll have a z mod p and a z mod p, but the claim is that I can tell the difference by the differentials. So dr will go to 0 for all r less than k, and then I'll have a dk connection here. And this will be an isomorphism. Suppose this is an isomorphism as well. So I just mean I have a non-zero map, right? Okay, so the whole point is that I can tell the difference between having just a copy of the integers mod p, having a copy of the integers, or mod p to the k, by looking at not only what groups do I have over here, but also what do my Bockstein differentials look like. Okay, maybe let me say that the proof, I won't go through in detail, but is really an easy exercise, and in fact you should do it in chasing diagrams. And maybe I'll just give you one example to get you started. So say you had a copy of the integers mod p, and we're looking at case 2, then in this diagram we'd have hn of x in mod p coefficients, mapping via beta to hn plus 1 of x. Then we've got our reduced mod p, and then here's our delta 2, right? And if I had a copy of z mod p, I should see this d1 differential or delta 2. Those are the same thing, and that should be an isomorphism. And how do I see that? Well, for the sake of clarity, let's just say it's only a z mod p there, so that I don't have to worry about everything else. I guess actually I should have started with only a z mod p here, and the next map out is times p, so that's going to map to 0 in this case. Again, not really if there are other groups there, but for simplicity, let's just say single z mod p. Okay, so that makes this map surjective. And of course, when I take z mod p and reduce mod p, I still just get z mod p. And so now I see that this differential is non-zero. This was z mod p. So in fact, it's that isomorphism. And we've proven sort of that middle thing in our chart above. Okay, so let me also say some terminology that goes with this. So let me scroll back just a little bit. What does our proposition say? The first piece is that if we had some integral class, but not just that, it generates a copy of the integers as a direct summand, then the differential is always 0, and it's never in the image of the differential. So I think this language has already come up for us, but I think it's worth being really explicit. We say this A bar here, the thing that shows up in the spectral sequence, is a permanent cycle. It's really like A bar, 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 and so on. So it's not exactly the same element in a sense, but we say it's a permanent cycle because dr is always 0. So what I mean by that is it shows up on every page in a sense, and it's never killed. And so, as we talked about, this is the kind of class that lives to the E infinity page. Now again, we haven't fully talked about different kinds of convergence and so on, but let's just assume that at some finite stage we have the E infinity page for the moment. Okay, and this B bar, now who is that? B bar was this class that generates a Z mod P as a direct summand in HM plus 1 of X in mod P coefficients, coming from this Z mod P to the K in integral coefficients. And so what we say here is that because this thing is hit by a differential, the dk differential, it's killed by B tilde. That's the thing that hit it. Okay, and we might also say B tilde supports a differential. Well, spelling backwards. Supports a differential. And sometimes we might be even more specific and say it supports that differential on the EK page. Okay, so again, remember we're taking classes of classes of classes of classes. So in a sense, this isn't a meaningful statement, but really I mean the class that is there because of B tilde. When we get to the EK page, it sees this differential, and so it supports that differential. Or that's what we say. Okay, so moral of the story. What can we say here? Well, if we know that we have this Bockstein spectral sequence, which again is just a tool for collecting long exact sequence information, so we didn't really need the whole machinery of a spectral sequence. If we just wanted to keep chasing things around in long exact sequences, we could. But if we know all of that stuff and we know the differentials, which can be a little annoying to chase around in the long exact sequences, well, then what are we going to find out? We'll learn about copies of the integers and copies of Z mod powers of P, and even precisely what powers we have in the cohomology of X in integral coefficients, maybe let's say from the cohomology of X in mod P coefficients. As I get towards the bottom here, it becomes less and less readable. Okay, but notice we're not going to see anything that looks like integers mod n for anything relatively prime to P. Okay, so this is one of the issues when I was talking about converging in some sense to the cohomology of X in integral coefficients. We're going to be missing a big chunk of it. If r prime is 2, we're never going to see any of the odd prime torsion. Okay, so I'll come back and address that a little bit more in the next video, and also look at the Bockstein spectral sequence in a different way.